So first of all, thank you very much to the organizer for the opportunity of speaking here in this conference. Today I would like to speak about a result on the spectrum of the Laplacian over compact stratified spaces that, restricted to compact smooth manifolds, gives a very well-known result, which is Obata-Lichnerowicz theorem for compact smooth manifold Ricci tensor bounded below. And in the second part of the talk, I will explain how this spectral result is related with the existence of conformal metrics with constant scalar curvature on a compact stratified space. So a very well-known fact in Riemannian geometry is that bounds on the curvature leads to a special behavior of the Laplacian and of its spectrum. For example, bounds on the sectional curvature give Laplacian comparison theorems, and bounds on the Ricci curvature gives the Obata-Lichnerowicz theorem, which reads as follows. So if we start with a compact smooth manifold whose Ricci tensor is bounded below by a positive constant, then we get the first non-zero eigenvalue of the Laplacian is bounded by below. Here everything is normalized with constant equal to n-1, so that the first non-zero eigenvalue is larger or equal than the dimension of the manifold. But of course we could have taken any positive constant. Moreover, we have a rigidity result when the lower bound for the spectrum is attained. The manifold must be isometric to a sphere. So the question I will try to answer in this talk is whether we can obtain a similar result for compact stratified spaces. One of the problems will be which is the good assumption on the curvature of the stratified space in order to get a lower bound on the spectrum. There will be an easier part. The part with the lower bound is much easier to prove than the part of the rigidity statement, but also the rigidity statement will be true for stratified spaces. So before, it will turn out also that the curvature condition depends on the angles along the stratum of codimension 2. So before explaining all these, I will fix the notation. We have already seen the precise definition of stratified space, but I will give a shortened one just to fix the notation for the rest of the talk. So here, a stratified space, a compact one, is a metric space which can be composed in two parts. One part, I will call it omega, is the smooth part, regular set, which is a manifold, open, dense in the whole space of dimension n. Then we have singular strata, and we consider strata that have codimension larger or equal than 2. So we are avoiding the possibility of having codimension 1 strata. And the behavior near a singular point is given by the following. So if we pick a point in the strata of dimension j, we will have an homeomorphism between a Euclidean ball of dimension j and a there will be a homeomorphism between a neighborhood of the point in the strata and the product between an Euclidean ball and a truncated cone over a compact stratified space, which is a link. In the case of dimension 2, the Euclidean ball here has dimension n-2, so we have only one possibility for the cone. It must be a two-dimensional cone, and so it's a cone over a circle. So in codimension 2, the link is always a circle. As for the metrics on stratified spaces, we consider admissible metrics. I won't go into the details, so let's start with a model metric. It's defined by induction on the complexity of the space, but let's say that if a model metric is a smooth Riemannian metric on the regular part of the stratified space, and near to the strata of dimension j, it will have the form of a product metric between a Riemannian metric on the Rj part and a cone metric over the truncated cone, where Kj is a metric on the link. Again, in the case of codimension 2, we have said that the link is just a circle, so we have an easy choice for the cone metric, which is a cone metric with an angle. So this parameter alpha here could be larger than 2 pi or smaller than 2 pi. And one important thing to know is that a cone of dimension 2 of angle smaller than 2 pi is an Alexander space with positive curvature, While if the angle is larger than 2 pi, we will have negative curvature. And if we want to get a lower bound on the spectrum, then we need to avoid the negative curvature. So we will have to avoid angles larger than 2 pi. More generally, we consider perturbation of the model metric, decaying with a good power of the radial function. But the important thing will be, in the case of dimension 2, having angle less than 2 pi. So we have all the tools that we need to give the curvature assumption that will lead to the Lichnerowicz theorem. So, still not. First of all, we can define the Sobolev space, W12, as the closure of Lipschitz function on the space. And since we have excluded the possibility of having codimension 1 strata, the smooth function with compass support on the regular set are dense in W12. So we can define also the Laplacian as the Friedrich extension of the good quadratic form on those smooth function. And it is self-adjoint, it has discrete spectrum, it has all the good properties. And then for a more geometric thing, if we pick a point in the singular stratum of dimension j, then we can define a tangent cone, which can be seen in two ways, either as a product between the Euclidean space and the cone over the link, or as an actual metric cone over the tangent sphere, which is a spherical suspension of the link. So now, as for the curvature assumption, we need something which is like Ricci tensor bounded below. So of course, where the Ricci tensor is defined, that is on the regular set, we assume that the Ricci tensor is bounded below by a positive constant, again here n-1 to normalize everything. And then along the stratum of codimension 2, with the maximal metric, we need that the angle is smaller or equal to 2 pi. So under this assumption of having a Ricci lower bound, we can prove the first eigenvalue of the Laplacian on a compact stratified space is larger or equal than the dimension. So this is the easy part, and it relies on the classical proof, which is with integration by parts and Wagner formula. And the main issue here is to have the good regularity on eigenfunctions, and then to choose cutoff functions in order to be able to integrate by parts. And some comments, if we drop the assumption that the angle is smaller than 2 pi, then we get counterexamples. So the theorem is not true for angle larger than 2 pi along the codimension 2 strata. In fact, if we consider just a spherical suspension, which is a double word product of a circle of length larger than 2 pi, then we can show that the first non-zero eigenvalue of the Laplacian is strictly smaller than the dimension. Another comment is that there was a Lichnerowicz singular theorem, but just for spherical cones. That means a word product over a compact smooth manifold with Ricci tensor bounded below, and this was due to Bakker and Sturm and proven with tools coming from optimal transport. So one of the consequences of this spectral gap is that we can deduce a Sobolev inequality with an explicit constant just depending on the dimension of the space and on its volume. And then by using this Sobolev constant that I won't write, we can apply some techniques due to Dominique Bacry and Michel Ledoux in order to get also an upper bound for the diameter of a stratified space with Ricci tensor bounded below. More precisely, we get that if the Ricci tensor is bounded below, then the diameter of the space must be less or equal than pi, and moreover, this upper bound is attained if and only if the lower bound on the spectrum is attained as well. And this restricted to compact smooth manifold gives Meyer's theorem, and it's an important step in order to get the rigidity results. So as for the rigidity, so what happens when the first eigenvalue is exactly equal to the dimension of the space? So we have that the lower bound on the spectrum of the Laplacian is attained if and only if our space is isometric to a word product between an interval and a stratified space of dimension n-1. So the proof of this rigidity statement is a bit involved. It relies on the study of geodesics in a stratified space, but I will try to give you some ideas. So first of all, the sketch of the proof is the following. There is one implication which is trivial. So if we start with a word product between an interval and a compact stratified space, we can write down an explicit eigenfunction for the Laplacian with the eigenvalue equal to n. And then what happens for the other implication? Let's suppose that we have a first eigenvalue equal to n, an eigenfunction relative to n. So the proof is by induction on the dimension and not on the complexity of the space, as we usually do. So in dimension n equal to 1, we have nothing to do because we just have a circle of length less than 2 pi. And then we assume that we have proven everything for dimension n minus 1, smaller than n minus 1. Then what we are going to do is that locally we show that the metric is a warp product. And then from the local result we pass to the result on the regular set. So on the regular part we get that the metric is a warp product, the one that we want. And finally we want to close everything because we have a compact space and get the result on the whole space. And the difficulties come most of all from the second step. So I will try to go a bit more into the details. So first we want that locally the metric is a word product. And the information we have is that there is an eigenfunction relative to n, and also there are 2 points that are antipodal thanks to the upper bound on the diameter, which is attained when we have an eigenfunction relative to n. So the guess is that this gamma, this stratified space of dimension n minus 1 appearing in the word product should be the zero level set of the eigenfunction. But of course, we do not know that this is a stratified space at the beginning. And what we do is that we pick a nice eigenfunction. So we have these 2 antipodal points, and as eigenfunction we can take the cosinus of the distance from one of the 2 points. So the picture is the following. We have Pn. So here, the zero level set of the eigenfunction is the set of points that are at distance pi over 2 from P. This is gamma. And then when I say locally the metric is a word product, will be locally near to points in this level set. So actually what we can do is that we start from a point here, which is in the smooth part of the stratified space. And near to this point, we can look at the flow of the gradient of the eigenfunction. So, which is well defined in a close neighborhood of the point and for some small interval. So there is a neighborhood in gamma 0, an interval 0 tx, in which we can consider this. And this time tx is the first time where we hit the singular set. Because of course we could hit the singular set. Nothing is saying that this flow remains regular. So in this small neighborhood, we just take the pullback of the metric and we get that it is a word product. Now the point is that with the singular set, and we would like to say that this tx is maximal and it is equal to pi over 2. So that we can arrive until here, the North Pole, and then extend the isometry on the whole interval minus pi over 2, pi over 2, sorry. So, and this is the second step in which we will use the induction hypothesis. So tx first time we hit sigma. So there, since we have taken closed neighborhoods, there exists a point such that the flow arrives in this x0. And we want to say that if this is smaller than pi over 2, then actually its 0 is regular. Because if it is regular, then we can keep on with the flow and arrive until the North Pole n. And in order to do that, we need to study the local geometry at x0. And the local geometry means that we need to study the tangent cone over the tangent sphere. And it is here that we use the induction hypothesis, because we can show that the tangent sphere has diameter pi so this is a word product, so the tangent cone splits, and finally, by using also the local information given by the first step, we can say that the tangent cone here is Rn. So the point x0 is in the regular set, and we can continue the flow. The interval is actually minus pi over 2, pi over 2, and then we can extend our isometry to the whole regular set. And finally, what we need is to close the interval, close this gamma 0, and get the isometry on the whole space. But it remains to say that this level set is a stratified space. And again, this is an argument using the tangent cone at n, because one can show that gamma is actually the tangent sphere at the North Pole, and we know that the tangent sphere is a stratified space. So we can conclude the proof. So some comments about that is that in dimension 2, the proof is easier, and it's due to Rafe and Armut-Weiss. Of course, in that case, a stratified space is, since we have now codimension 1 strata, it's just a surface with isolated conical singularities. And also, in a more general setting, Christian Ketterer has proven that an Obata-Lichnerowicz theorem holds on metric measure spaces satisfying an appropriate curvature dimension condition. And this uses the splitting theorem by Gigli, which is pretty complicated. But this was all I wanted to say about this theorem. And apart from the interest of getting a Riemannian result on stratified space with Riemannian tools, we have that this spectral theorem is related to finding a metric with constant scalar curvature on a stratified space. So the problem, I haven't written it, but it is in dimension larger than 3. It's the classical Young problem. So we start with an admissible metric on a compact stratified space, and we would like to know whether there is a conformal metric with constant scalar curvature. And this was studied most of all by Rafe, Gilles, and Katsuo. And thanks to their work, we know that the existence of a metric with constant scalar curvature depends on two conformal invariants, the Yamabe constant and the local Yamabe constant. So I will briefly introduce them. The Yamabe constant, we take the infimum over all conformal metrics of the integral of the scalar curvature, normalized by the good power of the volume. And then as for the local Yamabe constant, it is a bit more complicated to define, but let's say it. We take the Yamabe constant of a ball. It's exactly the same, but we restrict the infimum to conformal factors with compact support on the regular part of the ball. And then for the local Yamabe constant, we take the Yamabe constant of a ball of radius r. We make the radius goes to 0, and then we take the infimum over all the points of the space. So in 2012, Rafe, Katsuo, and Gilles proved that if the scalar curvature of the admissible metric is integrable enough, and if you have a strict inequality between the global Yamabe constant and the local one, then a metric with constant scalar curvature exists. The issue is that the value of the local Yamabe constant is in general unknown. And one of the important things in the Lichnerowicz theorem, which leads to a Sobolev inequality, is that it allows one to compute the local Yamabe constant in many cases. So first of all, the spectral bound and the Sobolev inequality that follows gives a lower bound for the Yamabe constant of a compact stratified space, Ricci tensor bounded below, which depends on the dimension and on the volume. And then, by using this, one can show that if the links carry an Einstein metric, which means that the Ricci tensor, the regular part, is proportional to the metric, then we can compute the local Yamabe constant. In particular, if we consider a simple case, so a compact stratified space with one stratum of codimension 2 and angles smaller than 2 pi along the stratum, then we have an explicit formula for the local Yamabe constant, which depends on a factor of the angle and the Yamabe constant of the sphere. And also, using also the Obata part of the theorem, so the rigidity statement, we can study the conformal class of an Einstein metric. And this is the last theorem I will talk about. So we start with a stratified space with Ricci tensor proportional to the metric on the regular part. So this is an Einstein metric, and we suppose that the angle along the stratum of codimension 2 is smaller than 2 pi. Then the Einstein metric attains the Yamabe constant. We already know that an Einstein metric has constant scalar curvature, but the main point here is that it is also minimizing. And also, if there are other conformal metrics which are non-trivial and have constant scalar curvature, the space need to be isometric to a word product, again between an interval and a space of dimension n-1. And this is done because if we take an Einstein metric, then the lower bound on the Yamabe constant is attained. And if we suppose that there are other conformal metrics with a conformal factor which is non-constant and with constant scalar curvature, then we can show that there exists an eigenfunction for the eigenvalue n. So we can apply the Obata theorem and get that the space is isometric to a word product. And this is all for today. Thank you very much for your attention.
Yeah, thank you very much again. Are there any questions? This time with microphone, please.
When the lower bound is 0. Let me think. Okay, so we can again get... I'm not sure. For RCD is also true when it is 0. I think it should be true for 0 too, but I need to think a bit more on the details, and then I will come back to you to say with a sure answer.
I have a question.
Yes.
Well, suppose that the eigenspace for the eigenvalue n has dimension larger than 1.
Mm-hmm.
Can you then, reduce your set of models? Get a stronger rigidity result.
If you have more than one eigenfunction.
If you have more than one eigenfunction.
I do not know where I would use it. I don't know.
Well, you used only one eigenfunction, right?
Yes, I used one, but
it might be an interesting question.
I never saying that it is the only one. I cannot say it is the only one.
Okay. Any other questions? Well, let's thank the speaker again.